All right, so in chapter 24, we're going to focus on aromatic substitution reactions, which are basically electrophilic aromatic substitution on benzene, as well as some other useful accompanying reactions. And that's really what we're going to settle down into in chapters 24 and 25. A lot of times, other books put these two chapters as one large chapter because they're so closely related. What you're going to see on this slide is a lot of polyurethane. Polyurethane is we can use it for a few things. We can use it as a clear coat on furniture. It's also can be used for things like skateboards. You can see the structure of polyurethane here. Now, polyurethane is typically made from aniline, which is shown right here, which is produced from benzene through reactions that we're going to study here in chapter 24. So let's go ahead and kind of start. Well, let's review some things about benzene before we get started. So a few things to remember about benzene is that the Lewis structure of benzene here contains 3 conjugated double bonds that are arranged in a ring. And so we might expect that benzene would undergo a electrophilic addition reaction like the different alkenes and alkynes that we saw in chapter 12 and 13, but it doesn't do this, right? And so we don't have any reaction when benzene is treated with hydrochloric acid or with Cl2 under normal conditions. Now, the lack of reactivity here is attributed to the stability of benzene's pi system. So, lack of reactivity is due to benzene's aromatic pi system, right? And this aromatic pi system just makes benzene very stable, okay? And so the addition of that HCl or Cl2 would disrupt the aromaticity, and that would convert benzene into a non-aromatic compound. And that's just not very favorable. However, right, and these, by the way, these would permanently disrupt benzene's aromaticity, okay? But look here. When metallic iron or iron 3 chloride is added to the reaction mixture with Cl2, benzene does react. Because the Cl in the product appears where there was initially an H, the net reaction is a substitution, not an addition. More specifically, this is called an electrophilic aromatic substitution reaction, which is sometimes called an EAS reaction, okay? And the reason it's called this is because an electrophilic chlorine, so in this case, it's an electrophilic chlorine, and an aromatic species are involved. So here in chapter 24, we're going to study the general mechanism for the reaction, for this reaction here, and then other electrophilic aromatic substitution reactions that involve benzene. And so these reaction mechanisms are really very similar. And so we're going to look at those. As a matter of fact, even though they vary in their reagents, the mechanisms are the same. Okay. Now, remember, aromaticity is not limited to benzene. Other aromatic compounds that we looked at in chapter 14 can also undergo electrophilic aromatic substitution. The mechanisms for the reactions involving other aromatic compounds are no different from the ones involving benzene, but they do require additional considerations of reaction rates and regiochemistry, which we are going to discuss in the next chapter. So in this chapter, we're going to focus on variations in reactions described by the electrophilic aromatic substitution mechanism. We are also going to consider organic synthesis, introducing reactions that are often used in conjugation, with electrophilic aromatic substitution reactions. So, without further ado, let's look at the mechanism. Right? Like alkenes and alkynes, the pi system of benzene is relatively electron rich, right? And so in contrast, an electrophile is relatively electron poor. So if we look at this general reaction, okay, here's benzene. And remember, benzene has hydrogens all around it like this. Now, instead of doing an electrophile, like a specific electrophile, we're just going to use E+ to represent a generic electrophile. And that positive charge emphasizes here that the electrophile is electron poor, okay? So an electrophilic addition step between benzene and an E+ results in a new bond, right? And this uses a pair of pi electrons from benzene. So these pi electrons from benzene come out and attack this electrophile. Now, this is step 1, which is the electrophilic addition. And there's a few things to keep in mind here. One of the key things to keep in mind is this first step here is slow. So it's the rate determining step. Okay, and some of the reasons that it's really slow is that your aromaticity is disrupted and a carbocation is produced. Now, the product that we get here okay, looks like this. Oh, I forgot a positive charge. Okay, and this is sometimes called an rhenium ion intermediate. An older name for this is a Wieland intermediate. So if you ever hear somebody talk about Wieland intermediate, but most people are trying to not use specific scientist names anymore. And an rhenium ion intermediate is more descriptive about what's actually formed. Now, this is a carbocation intermediate that consists of 5 sp2 hybridized carbon atoms and 1 sp3 hybridized carbon atom. Now, this intermediate will go on and participate, but it's really important to understand that this guy is resonance stabilized. And so because he's resonance stabilized, that's why this reaction can go on. And so what happens here in step 2 is that you have an electrophile elimination. Where a generic base, right, with a negative charge is going to come in and steal this proton, and then those electrons are going to go back here and form a double bond. And so through this reaction, we've restored aromaticity. And we've added the electrophile. Let me make sure that's a really nice bond there. So no more carbocation. So the carbocation is neutralized. And aromaticity is restored. So when we look at the free energy diagram, here, which was supposed to stay, I guess we will draw the free energy diagram. Okay, so we come here to the free energy diagram, right? And this is the reaction coordinate here. And right here at this level, we're going to have our benzene ring, right? And the electrophile. And then what we see here right, is here is our product, right? And then here is the uranium ion intermediate right there. And then what you can see here, right, is a really high energy transition state. Okay, so let me go back. The uranium ion intermediate is not aromatic, and so it possesses a positively charged carbon, right, that lacks an octet right here. So that means that this very first step is highly unfavorable. Now, by contrast, the elimination of the H plus from the sp3 hybridized carbon here, this step is highly favorable because it restores the aromaticity and gets rid of that carbocation. So, given the loss of aromaticity in the formation of a carbocation in step 1, you might wonder why an electrophilic or aromatic substitution takes place at all. And basically, the uranium ion intermediate, because it's stabilized by resonance delocalization of that positive charge, it is more stable than it otherwise would be. Okay, so resonance allows this to happen. So a few other things about this. This step 1 here, because it's a high energy transition state, is also the rate determining step. Okay, so when we think about this, right, in a general aromatic substitution reaction, it's first order with respect to the concentration of benzene and first order with the respect to the concentration of the electrophile. Now, just like reactions we've seen before, these are generally irreversible and take place under kinetic control. Okay. Now, the reason that both benzene and the rate depends on both benzene and the electrophile is because both of these appear in the rate determining step. And I want to remind you, in situations where electrophilic aromatic substitution is involved in a competition, it's really important to know whether it takes place under kinetic or thermodynamic control. And so what we know is that these reactions are generally under kinetic control. That means the thing that the reaction, if there's competitive reactions, the one that forms the fastest is the one that forms. Now, these substitutions tend to be highly favorable and irreversible because those electrophiles that are substituted for aromatic substitution tend to be very reactive and unstable to compensate for the disrupting that aromaticity of the ring. So in the next few sections, what we're going to do is introduce some specific types of substitution reactions. Each of these reactions involves the same two-step electrophilic aromatic substitution mechanism, but the identity of the electrophile differs from reaction to reaction. In most cases, the high reactivity required of each of these electrophiles generally makes it difficult or impossible to add them directly to the reactants. Instead, right, what we are going to find is that electrophiles in the electrophilic aromatic substitution reactions typically must be generated in situ from more stable precursors that can be added to the starting material. So as we look at these mechanisms, you need to pay particular attention to what the actual electrophile is and how it's generated, and you will have to show that as part of this mechanism. So let's look at the first one. The first one are halogenations. Now, recall from the introduction of this chapter that benzene doesn't react with molecular chlorine under normal conditions. In the presence of Fe or FeCl, chlorination does occur. Similarly, what we see here is benzene's not going to react with molecular bromine, but bromination will occur in the presence of the iron or iron bromide and produce bromobenzene, where that H, the hydrogen, is replaced by a bromine. Both of these reactions are examples of aromatic halogenation because a halogen replaces that aromatic hydrogen. Now, we're going to look at the bromination mechanism, but understand that the chlorination works in the same way, okay? And so when we look at this particular reaction, we draw iron bromide. Okay, and this is a Lewis acid catalyst, and then we're going to have the bromine right here, okay? And so these electrons are going to come here and attack that iron through a coordination reaction. Okay, and what it's going to form is this complex here. So let's look at some charges. Iron was uncharged before, it now has a negative charge. The bromine here now has a positive charge because it has two bonds. And then this bromine over here has 6 electrons. Now, understand something. This is strongly electrophilic. Because we have that positive charge. So what happens here is that the benzene is going to come in. Now, I'm not going to show all the hydrogens. I'm just going to show one. And it is going to come down, and these are going to attack, those electrons are going to attack that bromine because it's strongly electrophilic, and then those electrons are going to go back on that bromine. Now, that's our electrophilic addition. Reaction. And so this is where the aromaticity is lost. Now, what happens here, and I am going to shorten those 3 bromines to be Br3FeBr, and it still has a negative charge. And so what happens here are the bonds that make up this iron bromine bond come here and they attack that hydrogen, and then those electrons go around here to form a double bond through an electrophile elimination. Okay. And so when they do that, now we have the bromine that's been added. Now, you've got some other things here. You have FeBr3 and HBr. Notice that this is a catalyst, so it gets regenerated. So that's a Lewis acid catalyst that gets regenerated. The product is an aromatic this aromatic halogenation is an aryl halide, and this could be the desired target in a synthesis. Also, an aryl halide is particularly useful as a synthetic intermediate in the production of, say, a Grignard reagent. So that's why these become important. So, on that note, let's talk about synthesis. Show how to carry out this synthesis using an aromatic halogenation reaction. So when we look at the synthesis, you need to think what reaction can be used to form the necessary carbon-carbon bond. Now, that's the first question that he gives you. But I like to step back and I like to say, all right, look, what are we adding here? We have a benzene ring and we need to add this little bit right here on. So we have 6 carbons, and now over here we've got 1, 2, 3 more. So we need to add 3 carbons on. And so when we talk about forming when we talk about making this, we need to really focus on this particular part, okay? And then does that product of the reaction contain an appropriate functional group? Now, the new carbon-carbon bond here can be formed with a Grignard reaction, but if that happens, the product would be an alcohol. Okay, so go back and kind of, if you've forgotten that, go back and review Grignards, okay? And the target here is a ketone. So if we come here, and I might come down here, right? And we think about this through a retrosynthetic analysis view, we are going to undo an oxidation. To give us that, oh, that's a terrible bond, to give us that, okay? Then the next thing we need to think is, right, from what Grignard reagent and carbonyl compound could the alcohol be made? Now, when we look at this, right, we can disconnect the carbon-carbon bond between the carbon OH and the adjacent carbon, okay? So what I'm talking about is we could disconnect this one right here, okay? That's what we need to, that's where the disconnect falls in up here, right? And the Grignard reagent then could be made from the bromobenzene, which could be made by the halogenation of benzene. So we undo that, right? So we're going to undo a Grignard. And we're going to have this guy here. And then basically we're going to undo a Grignard formation. So undo Grignard reaction. Let's separate that out. Undo Grignard formation. To give us this. And then that goes all the way back, maybe, if I can get my iPad to work. Right, where we undo a bromination, and now we're here to the benzene. So if we now, so we've kind of thought through this, and now we can see here that we're going to present the synthesis. We would begin with the starting materials and then add the appropriate reagents as you go. And so that's how you would present the final synthesis. If that broke up a little bit, I had to pause it for a second. So now we're going to present this in the forward direction. We're going to present that final synthesis. So when we look at it, what we're going to see here is, here's our benzene ring. And we're going to add the Br2 and the Fe Br3. And then that gives us the bromine, right? And then to do the Grignard synthesis, we're going to add magnesium metal and we're going to stir it in ether. And that forms the Grignard, which is magnesium bromide like that. Then to add on the ketone, to form the alcohol, we're going to come here. Sorry, I said ketone and I meant aldehyde to form the alcohol. And add that and then the water. And then that will give us this alcohol. And then we're going to go through an oxidation with chromate in sulfuric acid. And that should give us our final product. So there we are. So that's how we can undergo a multi-step synthesis and use a bromination in this reaction. Now, we've talked about chlorines and we have talked about bromines. And so maybe the curious thought in your mind might be, what about the fluorination or idonation? Let me spell that. Well, it's spelled here for you because when I was making this slide, apparently I knew I would already have a problem with that. These proceed through a similar reaction. However, fluorine is really highly reactive. So generally you're going to use out, if you need to do a fluorination, you're going to use other reactions. Sometimes it tends to explode. Now, iodination can happen with one of the Lewis acids, but it's too slow. So generally what happens is it's carried out in the presence of an oxidizing agent like Cu2+. So this works as an oxidizing agent. Right? Like that, or hydrogen peroxide here, which is also an oxidizing agent. And basically what that does is it goes through and it just undergoes an oxidation reduction reaction where that's going to generate the I+, which then can enter into an electrophilic substitution reaction. So this works in a similar way. You're just going to generate the electrophile a little differently using either copper 2+ or hydrogen peroxide.